Now I want to talk about contracting implicit recurrent neural networks. This article in 2019. And the idea is that they propose an implicit model structure that allows for convex parametrization of stable models using contraction analysis of nonlinear systems. Using these stability conditions, they propose a new approach to model initialization and then provide a number of empirical results comparing the performance of our proposed model set to previous stable RNNs and vanilla RNNs. By carefully controlling stability in the model, they observe a significant increase in the speed of training and model performance. There are other paradigms as well. For example, if you know about reservoir computing, they have inputs and outputs, and here is a recurrent neural networks. But the thing is, we don't train these W's inside the weights. We just train the output weights, and we fix or randomize just W in and W, so that we only focus on W out and train this. And whenever we care about stability in recurrent neural networks, is because, for example, we want to model something in machine learning. It's a sequence, or even sequence to sequence. Then we have a stability. If we have a stability issue, if the trajectories, for example, get closer to each other, if we're starting from different initial conditions, it has some benefits. The advantage is that you can train that model even using backpropagation, anything. You can train it much easier, and their experiments have shown that. The importance of model stability has a more subtle implication than just safety. Because safety is, for example, in robotics, you care about stability, but it's more than that. It is closely related to difficulty in fitting models. Training recurrent model using gradient descent is complicated by exploding and vanishing gradient problems. If a model is too stable, the gradients will vanish. And if it is unstable, they will explode. So we don't want the model to be too stable, and we don't want it to be too unstable, something between, a trade-off. Just like the gravity constant and other constants in physics, if they are too high or if they are too low, the world will explode. We could not even exist. But if it is at a certain point, certain well-designed point, then it will converge and we can exist. So I've explained contraction analysis in previous lectures, so I just skipped them. But you know that, for example, there are many metric structures that we can use. For example, if we parameterize a quadratic form, this quadratic form where M is positive semi-definite, and X transpose MX, this means positive semi-definite, and or a positive definite, there is no equality. In this case, a sufficient condition for contraction is when we say this, it means that it is contract. It has contraction. It is just a sufficient condition. And for example, in this example, they can construct this metric, and this is the P in this previous slide. If you design P, which is diagonal of 1 and 10 in this simple example, which has only two states, then you will see that this system becomes contracting. They propose a class of contracting implicit recurrent neural network that is jointly convex in model parameters and stability certificates. The proposed set has less conservative stability conditions, which leads to greater expressibility when compared to previous stable recurrent neural networks, particularly in the multi-layer case. Additionally, they propose an initialization procedure that ensures both a rich set of dynamics, and the model is not too stable to train, which improves the model trainability. We then provide empirical result. So the explicit model is this. This is their explicit model. And F could be just an L-layer neural network with the skip connections even. And this theta refers to convex set we want to design. We can write the dynamics in this form. And we can also write the implicit model by just changing coordinate. So this is the implicit that you will see why it is important. So there is just this coordinate transformation that we need in order to create a different, the implicit model. And now you use the contraction theory and you say that in order to make sure that it is stable, you just need this inequality. And so the set of all CI RNNs, contraction, this stands for contraction implicit RNN, is this. So all theta, whenever your parameters lies in this space, then it is contracted. So theta is convex. And it is an intersection of many semi-definite cones. And so there exists the corresponding explicit model that I explained here. This explicit model. There exists this. So now we want to reduce. So you can even look at it as a system identification in nonlinear control systems and robotics, that you have a black box, you have a set of inputs and outputs. You want the output to be, the prediction to be as close as this prediction. But there is something. We compare this proposed the first is that we have a regular RNN, and the second is a stable RNN. So we have this linear matrix inequality in control systems, but here the U is our control. The things that, for example, that you are giving to an LSTM, some inputs, some tokens in natural language processing. These are your inputs that at given different time steps you give to this, and these are hidden states. And so this is your model. So no matter if you're working in nonlinear control systems or even in natural language processing, your problem is as general as just a nonlinear system with inputs. So you have model initialization. The interesting and efficient way is just to sample it, just using a normal distribution. If you sample it, just like the idea of reservoir computing, we just sample the input weights and also the internal weights, but we just design the W out using just simple regression. The idea is similar. The randomization, here we do this randomization again. But because the space of randomization is too general, you could have unstable dynamics suddenly explodes, or it is too stable. We don't want these two, because both of them, as I said, are extreme behaviors. We don't want to explode. We don't want to be too stable. We want something to be normal, something between that has good stability properties, but that is good for training our recurrent neural networks. In order to do that, to make sure that our initialization does not ruin everything, we design theta such that our AE is equal to W. Because if you multiply E to the both sides, this becomes AL, EL equal to WL. So this is just, if you reduce it, it becomes this. So this becomes AL minus 1 minus WL equal to 0. So if this term is minimized, so this is what we are doing here, then we have achieved that. So we make sure it generates, we make sure that we project into stable sort of contracting implicit models. That I showed you what are the conditions of that contraction. So everything is now ready for the optimizer. For example, they use Atom Optimizer to minimize the cost. And their cost is just this one that they use for system identification or anything in natural language processing, and plus another term. So they designed the C to be, this one are equality constraints. So we use an initial learning rate which decays by a factor of 0.96 at each epoch.